Good afternoon. We are going to review the converse of the Pythagorean theorem, which is used to determine what type of triangle you're looking at. So this little chart gives you a kind of a nice review. I'm going to put the form of the equation that you're probably more used to up above. So your Pythagorean theorem converse, first one is right angled. If you have a triangle that has a right angle in it, then a squared plus b squared equals c squared. Leg plus leg has to be equal to the hypotenuse squared. And the converse says if leg squared plus leg squared equals hypotenuse squared, then you have a triangle. So where this really takes off is with obtuse and acute angled. If a squared plus b squared is smaller than c squared, it means c must be gigantic. This obtuse angle here has to be greater than 90 degrees, so you're going to have an obtuse angled triangle. So if c is really big, that tells you you've got an obtuse. Okay, if a squared plus b squared is larger than c squared, so c, which is supposed to be the longest side, is actually quite small, then you have an acute angled triangle because the largest angle is not all that big. Now for an acute triangle, remember that all three angles of an acute triangle are less than 90. So this gives you a great way to figure out the type of triangle you have and the kind of math you will need. So let's practice that. But before we do, there's one more consideration, and that is, given sides, is a triangle possible? There are some side lengths that don't give you enough length to make a triangle. And so there's three situations you can run into for a triangle not being possible. One of them is if, let's say this is your C, if your A and your B are really, really small, they'll fall flat. They won't even make a triangle at all. If A and B together are the exact same length as C, they're still going to fall flat. So, in summary, A plus B has to be bigger than C for a triangle to be possible. So here's A, here's B. They're going to meet up and actually make a triangle. So that's how you test if a triangle is possible. Does A plus B, is that greater than C? If it is, you're in business. Okay, so let's look at these triangles. We're going to start with triangle A. And for all triangles, you want to make sure that a triangle is actually possible, which you can usually do in your head. 8 and 9 are the small sides, so 8 plus 9 is 17. That is greater than 10, so a triangle is possible. That's the first thing you want to do, is add the two small sides, make sure they're bigger than the big side. Now we're going to use our converse. We're going to take small side squared plus the other small side squared, and we want to know what is the relationship between those two and the big side squared. Notice that when you're proving the triangle is even possible, nothing is squared. When you're trying to figure out the type of triangle, everything is squared. Well, this is 64 plus 81, which ends up being 145. 10 squared is 100. 145 is bigger than 100, which means that that C, that long side, wasn't very long. So this is an acute triangle because A squared plus B squared was bigger than C squared. Okay, let's look at triangle B. First, let's check and see if a triangle is even possible. The small sides are 12 and 5, so 12 plus 5 is 17. 17 is greater than 13, so we're good to go for the triangle. Now let's figure out the type. We're going to take small side squared plus the other small side squared. What is the relationship to the biggest side squared. Well, 5 squared is 25, 12 squared is 144. Add them together, you get 169. 13 squared is also 169. So they are equal, which means this is a right triangle, because a squared plus b squared was equal to exactly c squared. All right, let's look at triangle C. So triangle C is kind of interesting because you really do need to know what square root of 3 is. Square root of 3 is something like 1.8, 1.9, something like that. So you actually do have a triangle that's possible. Let's do the test though. We're going to do radical 3 squared plus other small side 1 squared. What is the relationship between that and 2 squared? Well, radical 3 times radical 3 is a 3 plus 1, which is a 4. And 2 squared is 4. They are equal, so you have a right triangle. Let me give you a better number for that radical 3. I feel bad, my estimate was off. Square root 3 is 1. Yeah, I was right, 1.7. That's about right. Okay, let's do triangle D. All right, 24, let's check to see if a triangle is possible. 24 plus 7 is 31. That's bigger than 25, so we're good to go. The triangle is possible. Now we're going to see what type it is. So take small side 7 squared plus the other small side 24 squared. We want to compare that to the big side squared, 25 squared. So 7 squared plus 24 squared ends up being 625. 25 squared is also 625. They are equal to each other, so it is a right triangle. Okay, last one we're going to do is E. We're going to do the obtuse. Whoops, I gave it away. Let's try E. First, make sure a triangle is possible. 13 plus 6 is 19. That is bigger than 15, so we're good. Now we try small side, 6 squared, plus the other small side, 13 squared. We want to know what is the relationship between that and the longest side squared. So we get 36 plus 169. It ends up being 205. 15 squared is 225. So c squared is bigger than a squared plus b squared, which means c must be really large, which is why it is an obtuse triangle. So always test to see if a triangle is possible, and then use the converse of the Pythagorean to tell you what type it is. Okay, flip the page. Okay, Hypotenuse Leg Theorem. This is the triangle congruence theorem that is only good for right triangles, but it's a really nice shortcut to other ways. So here we go. It says, if the hypotenuse and one leg of a right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. So this one is unique. All the other theorems and postulates we learned, you had to have 3 things true. Side, 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 angle, angle. All of them had 3. This one doesn't. There's only 2 things that have to be true, hypotenuse and leg, but the caveat is they both have to be right triangles already. So there is an abbreviated form of this, which is kind of nice. Okay, so here's an example. Triangles ABC and ZXY are right triangles. Hypotenuse AB, here 1 tick mark, is congruent to hypotenuse ZX. We got that off the drawing. So that is your hypotenuse, and we have a leg. Leg AC is congruent to leg ZY. So I have right triangles, the hypotenuses are congruent, and a leg is congruent. Then the triangles are congruent by hypotenuse leg theorem. That's usually your abbreviation for hypotenuse leg theorem. Okay, example 1. What information is needed in order to apply the hypotenuse leg theorem? So I've got right triangles, so that's good. I have a short side here, QR, but I would need that short side also. So I'd need to know that MN was 5. That's the leg. Now the hypotenuse. I have hypotenuse LN as 9. I would need this hypotenuse to also be a 9. So PR would have to be 9 in order for this to be congruent by hypotenuse leg theorem. I would need both hypotenuses and both legs. All right, number 2, error analysis. Yama stated that triangle KLM is congruent to triangle PLN by the hypotenuse leg theorem. What mistake did Yama make? Okay, so what's a little deceiving about this is the fact that they look like they're right triangles, but it doesn't actually say that they're right triangles, and hypotenuse leg is only good for right triangles. So the problem is here and here. We have what looks like a hypotenuse that matches and a leg that matches, but we don't have right triangles. So what mistake did she make? She needed the measure of angle NLP to be equal to 90 degrees and the measure of angle MLK to equal 90 degrees. So they are right triangles. So it wasn't enough to know that they are congruent. They had to be 90 in order to use hypotenuse leg. Okay. Identify congruent triangles. Is it possible to prove that the triangles are congruent? If so, state the postulates or theorems that you would use. Okay, so we do have two parallel lines. If we look at this transversal, that would give us E and B being congruent. If we look at this transversal, that would give us A and D congruent. And vertical angles are congruent would give us this one and this one. So we have three angles but no sides. Unfortunately, there is no angle theorem. So the answer would be no. It's not possible to prove those are congruent because there is no angle. You got to have at least one side. Okay, so let's look at this one. We have TU and TW, so we have a side. We have UX and XW. We have another side. And if we ignore these two lines here and use this as our third side, TX is shared. So we can say that TX is congruent to TX because of the reflexive property. And that would give us three sides. So we could prove it that those two big triangles are congruent by side, using reflexive property. All right, let's look at this one. Okay, I have a short side here and a short side here. Okay, that's good. I have a 90-degree angle here and a 90-degree angle there. So they are right triangles. But I need another side. I need the hypotenuses to be congruent before I can use hypotenuse leg. So, sorry about the telephone ringing. So that's the sides that I need. So in this case, we're going to say no triangle is possible. And if they asked us why, we would say to use hypotenuse leg, we need to know that ML is congruent to NP. Anyway, okay, so that one, no triangle is possible because we need the hypotenuse to be the last side. All right, that is what I have for you today. Have a wonderful afternoon. Goodbye.